That's loud. Okay. Okay. All right. So my name's Joe de Carolis. I'm an assistant professor at North Carolina State University in the U.S. And first, I'd like to thank the hosts. I think it's been a tremendous event. It's an honor to be here, and I've learned a tremendous amount. So first, I want to thank them. And what I want to do today is, I guess, a little bit different than the other talks. I want to talk more about the process of developing scenarios and take you through some of the things that I've learned over the last roughly 10 years being an energy system modeler. When I graduated, I worked for about 3.5 years at the Environmental Protection Agency in the US, and then I transitioned to an academic position. So I'm not going to be presenting any model results, okay? And I'm not going to be talking about the collapse of civilization. So, all right. So there's three basic components to the talk. One is just a very quick introduction to energy economy optimization models, and then I want to talk about what I think the problems are with the status quo in terms of how those models are applied, and present some recommendations on how to fix what I see are some problems. And then I'll spend a little bit of time talking about some of the work I've been doing to develop a new open source model and how we've implemented some of the recommendations we make. So you've seen a lot of language like this, but I think it's always important when you give a talk to motivate where you're coming from. So why do I care about energy modeling? Why do I bother? And in the long run, these are the kinds of things that I'd like to help address, right? The same kind of things I think we're all here to talk about. So how does the world balance the cost of greenhouse gas mitigation in the near term versus the long term? What are the anticipated economic and environmental impacts associated with future environmental policies? How does that result in different energy technology deployment? This one is, I think, pretty important. How do we inform decision makers and allow them to craft policies that are robust to future uncertainty? And we have very large irreducible uncertainties to contend with. And then finally, how do we also help inform decision makers so that they can take account of broader sustainability considerations beyond just simply limiting greenhouse gas emissions? So we need some way to organize all of this information, and one of the ways that we can do that is with these energy economy optimization models, okay? And what the models do, it's kind of a catch-all term that I came up with just to capture the range of different models that are out there. They're optimization models, that's in the title. So they're either minimizing cost or maximizing utility. And they're at least in part doing that by optimizing the energy system over multiple decades. Okay? And they have a few important characteristics. One is they're a self-consistent framework for evaluation. We put the data in. We have a set of rules that we devise about how that data is manipulated. We can explore how particular effects propagate through the whole energy system. And we're building the models so that they have pretty expansive system boundaries. It might be regional, national, it could be global. And we're often looking over timescales that span multiple decades. And one thing I want to be clear about, these models are not going to give the answer, right? Because the answer to the questions that I pose are not strictly technical or scientific. It's really a mix of technical, economic, and moral considerations. But I do think that these models can help inform some of the decisions that we need to make. And again, the bottom line for me is when we run these models, what can we usefully conclude? What insights can we develop when we rigorously quantify the uncertainty? So just to give you a little bit of my mindset and the kind of modeling that I'm most familiar with, most of my work is with technology explicit models, okay? And this is just a simple little example. Don't worry about what all the labels are. The green boxes are processes or technologies, okay? The blue dots are commodities. And the arrows represent commodity flows between different technologies, okay? So the way that they're referred to as technology explicit models because we're actually representing individual technologies, not necessarily individual power plants, but individual classes of technology. And for each technology, we specify all of these engineering economic parameters. Okay, so things like capital cost, fixed O&M, variable O&M, operations and maintenance cost. What's the capacity factor? What's the conversion efficiency? If it emits, how much is it emitting per unit energy produced? Okay, so this is our self-consistent framework. And it's an optimization model, which means it has to have an objective function. And the objective function is simply to minimize the present cost of energy supply over a defined time horizon. Okay? So this is simple microeconomics. We do use a discount rate because we need some way to compare future costs to present costs. The decision variables are generally the activity of each technology, and really that's just a term to mean what's the throughput of each technology, and the capacity. So we might have some throughput, but we also have some maximum capacity for each of these technologies. Okay, so that's roughly how the models work. I don't want to go into a whole lot of detail on the formulation, but hopefully that gives you a relatively good sense for how these types of models work. If you've heard of the Markal model, the Times model, they're examples of technology explicit models. Message is another one. And they've been used to produce some pretty high visibility analyses. So other folks have mentioned the IPCC special report on emission scenarios. Every other year, the International Energy Agency produces the Energy Technology Perspectives report with a big, they have a large Markal model. And then in the US, we have the Annual Energy Outlook, which is the official midterm energy forecast of the US government. It's produced with a large energy system model called NEMS. And then the US EPA does legislative analyses. So if there's a member of Congress who's proposing a bill, they'll send the key components of the bill to EPA and say, hey, analyze this, tell me what the impacts are. Okay? And they use energy economy optimization models to do that. Okay?
It's a formal process, or it's just the way it's done?
What do you mean formal process?
The fact that EPA does legislative analysis, it's an obligation?
Yes, it's an obligation. They get a formal request from a member of Congress saying, please do this, and they do it. I mean, I don't know what would happen if they didn't, but so I think it is. I think it's formal. Yes, it's one of their responsibilities. So I mentioned I've been doing energy system modeling for about 10 years, both at EPA and now at NC State, and every year I go to energy conferences. The primary one, by the way, is the International Energy Workshop, which is where all the energy modelers from around the world gather. And I don't know, a lot of times I would just have negative reactions to a lot of the presentations and the way the analysis was done. And when I came to NC State and I was thinking about how to develop my research program, I wanted to sit down and try and diagnose what it was that was bothering me about a lot of the work that I saw. And so this is what I came up with. So this is kind of overall, I'll just describe the components and then I'm going to step through them one by one. Okay? So starting on the left-hand side, we have an inability to validate model results. Okay? And again, I'll explain in more detail why I think that's true. That goes along with two things that are actually should be positive. One is increasing availability of data. That's a good thing. In Moore's law, we have, over time, greater computing power, right? So things that we couldn't do 10 years ago in terms of analysis, now we can do. So these two items are good, but when combined with the inability to validate model results, it leads to increasing model complexity, okay? Increasing model complexity coupled with the fact that many of these models are not open leads to two very detrimental effects, in my opinion. One is the inability to verify model results. So if I publish a paper with a set of results that might have some pretty strong implications for policy, do you just trust my results? There's really no way to replicate the results. And again, I'll get into more of that, unless we make everything available. And then finally, if you have more complex models, it makes uncertainty analysis more difficult. And again, I think that's where we need to really focus effort because we have really large uncertainties that we need to try and deal with and that decision makers want to understand better in the decision-making process. Okay, we've talked a fair amount through the week about validation. And when I was doing my work, I came across a report that was written by a couple folks at the RAND Corporation, which is a US think tank that does mainly military consulting work, okay? And they were mainly concerned with military models, everything from fuse activation to models of theater level combat. And there was lots of arguments about how to validate the models. And what they said was, look, first of all, not all models can be validated. And if you want to have a model, if you think you have a model that can be validated, it needs to meet these conditions, okay? So the first is, it must be possible to observe and measure the situation being modeled. Second, the situation being modeled must exhibit a constancy of structure and time. The situation being modeled must exhibit constancy across variations and conditions not specified in the model. And lastly, it must be possible to collect ample data with which to make predictive tests of the model. Okay? Now, I think that everything that they wrote about is perfectly applicable to the kinds of models that I run. And I would venture to say that pretty much any energy projections that involve some component of human behavior should be subject to the same set of conditions. And I know with my model, it fails at least 3 of the 4 conditions, okay? Arguably, maybe we can collect enough data. That's questionable, but I think it fails these other 3, okay? The first one, it's possible to observe and measure the situation being modeled. Well, if I'm really interested in what the long-run implications or outcomes are, I just basically, let's say I'm projecting to mid-century. What do? Wait to mid-century to validate my model? I do have the data, but I have to wait so long that practically this isn't going to help me improve my projections, okay? Second, the situation being modeled must exhibit a constancy of structure and time. It kind of fails that condition as well because we have large changes in energy markets around the world. We have new conditions. So for example, after the OPEC oil embargo created a new set of conditions. In the US, we've had deregulation of electricity markets. These are things that I don't capture, and most modelers that I know can't capture. So the situation that we're trying to model doesn't exhibit a constancy of structure and time. And then finally, the situation being modeled must exhibit constancy across variations and conditions not specified in the model. Well, all models are simplifications of reality, and there are certainly real-world things going on that we can't capture in the model, so this is not true either. So I would argue that the type of models that I run, and again, most of the models that involve energy projections over a long period of time fail these conditions, and they cannot be validated, okay? So, I'm free to entertain thoughts to the contrary, but that's my thinking, okay? What they say is if you can't validate the model, then don't use it for predictive purposes, right? So don't use the kind of model I run and say that the price of oil in 2050 is going to be $130 a barrel, okay? Yeah.
How about trying to validate them by looking backwards?
Yes, I've thought a lot about that. So you can do backcasting exercises, right? So I could start the model in 1950 and then project to, say, 2010. But the problem is that I still have the knowledge of what happened, so I can tune the model to try and capture some of those things. And if I tune it so that it performs very well for that backcasting exercise, there's absolutely no guarantee that it'll perform well moving forward, say from 2010 to 2050 or 2060. So backcasting exercises might, there's some utility in doing it, but I would argue that it's not the same as validating the model because of these two issues. You have variations and things that are taking place over time, and being good at predicting the past is no guarantee that it'll work well in the future.
Just almost something.
Yeah.
What I see here is that even beyond that, I think it's an optimization model that, look, it's a normative.
Yeah.
And it makes the assumption that there's one single decision maker that has all the decision power on all the system and makes its decision on one single criteria that is the optimization of the system.
Yep.
That's not what happens in the real world.
Of course, right.
So there's
Right.
There's no reason why such a model could reproduce the
That's right.
try to-
That's right. But that doesn't mean that but people are putting it to that use. And I think that's what we have to be careful of.
We keep the question
Okay,
for
sure,
after.
sure.
Only if there is a point you don't understand and you need that to go on understanding, then you ask a question.
Okay, so the good news is it doesn't mean that if you have a model that's, that can't be validated, that it's worthless, okay? Here are some examples of things that they say you can do with a model that can't be validated. One is use it as a bookkeeping device, right? Gather data, organize it. It can be an aid in selling an idea, of which the model is but an illustration, right? So we want to advocate some policy, we use the model. It can be an aid in communication. So if you're trying to communicate, for example, the complexity associated with, implementing a particular policy or pushing the deployment of a particular technology, you can use the model as an aid to communicate how perhaps complex the system is and the fact that there might be system effects. It could be used as a vehicle to make comparisons. So I might not be projecting a particular value, but I might be able to say, well, option A looks better than option B. Okay? And this last one is also important. It's an aid in thinking and hypothesizing. The person who learns the most from a model is the person who is actually implementing and running the model. Right? That's always true. So it helps us think about the future. And the one that I would add is I do think it's possible to run energy models under a lot of different scenarios and try and identify robust outcomes. Okay, so if I'm doing a particular analysis and let's say I do a Monte Carlo sensitivity analysis where I treat a bunch of parameters with uncertainty and I'm looking at the electricity sector somewhere, and I find that, out of 10,000 scenarios, 95% of them have a large deployment of wind power, then I might conclude that, wind power is going to play a large role in our future. Okay? That's very different than saying the installed capacity of wind in the US in 2050 will be, 200.6 gigawatts. Right? All right, so that's the validation issue. Now moving to model complexity. Now again, this is just my observation, being involved in this for a while. First, I want to make a distinction between structural and parametric uncertainty. Structural uncertainty is just the idea that the model itself doesn't represent reality, that the mathematical equations are a simplification of reality, right? So that's where the structural uncertainty comes in. The parametric uncertainty is that the data that goes into the model is imperfect, okay? So we can't validate the models, and as a result, people keep adding complexity to the models, but they have no idea whether the complexity actually helps them generate the insight that they're after, right? It's just if you're doing energy modeling, you present some results, and then what are you going to do the next year? You might change topics, but one of the things that people do is they just make the models more complex, okay?
Excuse me.
Yeah.
Can you explain what you mean by validating?
Validation okay, so let me give you an example of where I think validation works well. Take weather models, okay? I can run a weather model and then observe the actual real world outcome, and then I can perhaps tune the model, add variations to it, different equations, try it again. Does the prediction work better? So I can determine by comparing the model result to actual real world outcomes whether or not the model skill is increasing based on something that I'm tweaking in the model. And I would argue that that's not something that we can do with energy system models.
So excuse me,
Yeah.
just a clarification. So you mean that you are dealing with models that pretend that they are just trying to predict reality? You are
Yeah.
taking as an example weather forecasts.
Mhm.
And all know here that weather is something that we try to forecast. But in the framework of energy modeling, the question is not to forecast.
Correct, which is exactly the point. You can't, and the argument I'm making is because you can't validate, you shouldn't treat them as a forecast.
So if you are not forecasting, there is no reason to try to validate.
Correct. Well, I mean, but think about it. If you could validate, wouldn't you? Why would you not? I mean, I would certainly try it as a modeler, right? If I actually knew what the outcome in 2050 was, absolutely I would do it. I would want to know what kind of scale my model has.
I mean, you may want to validate when you try to rerun the model
Yeah.
that is in front of you and find the same results.
Yeah.
Then the one the authors pretend he has found. Okay, so it's kind of validation.
Yeah, but I think my definition of validation is that you can compare it to an actual real world outcome, not to somebody else's model. You know, it has to be to a real world condition. Okay.
I propose we go on this discussion after one because it's important. It's an important question.
Yeah.
Well, it's not only clarification. It's just okay.
Okay. So what I argue is that because the models can't be validated, whether or not modelers really realize that or have thought about it formally, what it means is that there's nothing to really guide modelers that rein in efforts that don't improve model performance. So I could just make the models more and more complicated and, ooh, you know, wow, this is really interesting. Now you have a 30 region model, you have endogenous technological learning, you know, blah, 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 and it all sounds very impressive. But we don't actually know whether some of that complexity improves the projections, okay? And the more complex you make the model, the harder it is to do sensitivity and uncertainty analysis because you're weighed down by this complex model. And the fact that we can't validate is kind of obvious in the results that we've gotten with the model. So here are two examples that show how pretty poor the models actually are at prediction. Okay, so this is a projection by the US Atomic Energy Commission in 1962. They were trying to predict how much nuclear we were going to have in the year 2000. And they projected almost a terawatt of nuclear power, and the actual number was about 100 gigawatts, so off by an order of magnitude. Okay? Here's another example where all of these dots and the lines represent different studies. This is the year in which the study was conducted, and this is their estimate for primary energy consumption in the US in the year 2000. This is what it actually was, and this is what all the projections said it was. So nobody even under-predicted. Everybody over-predicted, and it's really funny if you look in the later studies. I mean, they're marching towards the right answer, but they're still way too conservative. Okay, so again, the models generally don't have a good track record of prediction, and part of the reason is because they can't be validated. Okay, so there's also, in my experience, a strong lack of openness. I think this is starting to change. I'm starting to see a shift in the last couple of years, but I think it's still this effect is still fairly strong. And I do think there are some good reasons for keeping things closed, listed here. But in the end, I don't think that we should. I don't think that these reasons are strong enough to keep the models and the data closed. So we have protection of intellectual property, right? I invested X number of years in this. I'm not just going to give it away so other people can do the analysis that I might want to do. There's fear of misuse, right? Somebody who doesn't know what they're doing takes your pretty sophisticated model, does something stupid with it, and then it makes you look bad because they're using your model. Right? There might be implicit commitment to provide support to users. So you make this thing publicly available, you start getting streams of emails about I don't know how to install it, and what happens if I get this number, and so it's just a headache. Overhead associated with maintenance, you might have to keep it online, so do you have to pay for a web server and things like that, maintain a database. And then people are generally uneasy about subjecting code and data to public scrutiny, right? And chances are, given how complex the models are and how much data goes in, there are errors, and so you don't necessarily want people nosing through all of the work that you did. Okay? So this leads to an inability to verify model results. So the models are complex. What that means is if I write a journal paper, even if I have an appendix, and maybe I even have separate model documentation, the models are complicated enough that I cannot use that information to reproduce the results from a particular published analysis. And I would argue that reproducibility of results is fundamental to science. And the only way that we can overcome this issue of verification is if we make the source code and the data associated with the models open source so that everybody has access to it. Okay? You know, when I was thinking about replication, I have my undergraduate degree is in physics. So, you know, replication, the ability to repeat scientific experiments is something that I think we all understand very well. But I wanted to dig a little bit deeper and understand why is repeatability why was it so important, and what are the analogs to today with energy modeling. And, you know, when I went back and started digging into the history of science a little bit, it turns out that during the scientific revolution of the 17th century, prior to what they were contending with was basically Aristotle's natural philosophy, which didn't rely on experiments. The idea was, you know, Aristotle's a smart guy. He sat down and could think essentially about how the world works, okay? And so you have scientists, the first almost generation of scientists coming along who are conducting experiments that might contradict something that Aristotle wrote. And people don't want, I mean, they're used to natural philosophy. They're not accustomed to thinking about experiments, okay? So a good example was Galileo. He figured out that the distance traversed by an object in free fall is proportional to the amount of time spent in free fall squared, okay? Well, that seems kind of like a random and specific observation, so he set about proving it. So he devised these very careful experiments where he could demonstrate that, in fact, this was true. And he referred to it as, I'm kind of paraphrasing, but making memories of the same thing. Okay? He wanted to show and demonstrate clearly that what he was saying was correct. Right? And that was the only way that science could triumph over natural philosophy, was by proving it to people. Okay, so again, the purpose was to convince skeptics that a counterintuitive result could be obtained by following a prescribed procedure. And really, this repeatability criterion, I think, is common to all forms of reason-based inquiry. Right? If we want to prove something to someone else, then what we're saying ought to be repeatable. Okay? So I think it's particularly relevant to energy and climate-related policy analysis, especially since we're potentially talking about the transfer of huge sums of wealth. Right? I ought to be able to demonstrate how my model works. All right, and then finally, uncertainty analysis is difficult, again, because the models are fairly complex. And a common result is false precision. So we just pretend that there's not so much uncertainty. And so I've actually seen there's EPA analysis. This is of a particular climate bill that was introduced in the US Senate, where they provide growth estimates for the gross domestic product down to 1/100%. I mean, there's no way, right, that they know it to that level of specificity, but they run the model and, you know, the model gives them the number and so they use it. Okay, so there's a lot of that false precision out there. As a result, large complex models are tuned to look at a few scenarios by necessity, right? Because computationally it's pretty intensive. I would argue that scenario analysis is often overused, right? So for any issue that we want to study, we run on the order of 5 scenarios and that's it, right? This is the extent of it. The other thing is when we generate different scenarios, we're not telling a decision maker anything about what we think the subjective probability is, right? So if you take on the standpoint of a decision maker and you present them with 5 radically different ways in which the future might unfold, I mean, how do they make a decision? Because they have to make the decision before the uncertainty is resolved. So maybe we need to think more about, you know, assigning probabilities to some of these scenarios. Now, there's also some other problems with scenario analysis that we all need to be aware of, okay? And it's not necessary, I'm not suggesting we stop doing scenario analysis, but I think we need to be aware of some of the issues. And there are some well-known cognitive heuristics that play a role in how people interpret the results of scenarios, okay? So 2 examples of cognitive heuristics, basically the human psychology of how people process information. One is the availability heuristic, and that is the probability of future events the probabilities of a future event or outcome assessed on the basis of how easily an individual can remember or imagine examples. So, for example, if you ask the average person the probability of dying in a plane crash, right? Every time a plane crashes, it's on the news, right? So it's very easy to recall those instances, and so they tend to overestimate the probability of dying in a plane crash, right? Because it's easy to recall all the times where it did happen, even though it happens very infrequently. Another example is called anchoring and adjustment. You give people a bit of data or an initial value, and that serves as an anchor. When you give them additional information that should perhaps change their viewpoint, they generally don't adjust their position enough, right? So in the face of additional information, they anchor on that initial piece of information you gave them, and they don't make the proper adjustments given new information. And what all of this means is that if you provide a few highly detailed scenarios, they can create very cognitively compelling storylines. Okay? And this is, by the way, detailed in this paper. David Keith was my PhD advisor. Okay? So they go into a lot more detail about all of this. Okay? So here's an example of the availability heuristic and why this and how this works. So I apologize. This plays off of lots of different stereotypes. This is drawn from a paper that was published in 1976 by Paul Slovic. So let me just read this scenario to you. Okay, Tom is of high intelligence, although lacking in true creativity. He has a need for order and clarity and for neat and tidy systems in which every detail finds its appropriate place. His writing is rather dull and mechanical, occasionally enlivened by somewhat corny puns and by flashes of imagination of the scientific type. He has a strong drive for competence. He seems to have little feel or little sympathy for other people and does not enjoy interacting with others. Okay? Now, I apologize. It plays off stereotypes. So, a bunch of people were given this description and then given these three scenarios. Okay? So the first one is, Tom will select journalism as his college major. 2, Tom will select journalism as his college major but become unhappy with his choice. And the third is, Tom will select journalism as his college major but become unhappy with his choice and switch to engineering. Okay? Now, this is a learned audience. So what the people who participated in the study were asked is, which of these scenarios is most probable?
3 contains 2 and 1 and 2 contains
1 is the most probable because it has the least amount of information, right? When you move from 1 to 2, you're making an additional assumption. When you move from 2 to 3, you're making another assumption on top of that, right?
Yeah, but most people are just looking for the word engineering.
The point is, they've done this experiment many, many times, using different, different scenarios, and people gravitate towards the answers that contain the most information. Okay? So again, relating this back to the type of energy scenarios that we develop, if you're interacting with a decision maker and you provide a great amount of detail about each scenario, it's our tendency to assume that the world can only unfold in the 5 ways that you've articulated. It's hard to imagine possibilities outside of what you've articulated. Okay? And again, it's just important to keep in mind. So what should we do? And a lot of the recommendations here that I present were published in a paper with my graduate students in 2012. So the first recommendation is to make source code publicly accessible. Right? Just publish the source code for the models. There's a nice paper in Nature where they argued that even unambiguous descriptions of code using natural language do not lead to, there's no guarantee of reproducibility. So I can't just qualitatively describe computer code and expect that that's going to allow someone to recreate my model and my results. Okay? Use, these two kind of go together, but use software configuration management and revision control systems to track changes to code. Okay? This is very common for software developers. They do this. This is standard practice. Okay? We don't really do it as much with modelers, but it's important, right? You might get one result and then you go in and modify the equations, and then all of a sudden you start getting different results, and wait, who made that change, and when was it made, and why did we do it again? If you use tools like this, it allows you to track, to basically audit all of the changes to the model. Anytime you change the code, you have to provide a commit message that says exactly what it is that you did, okay? And if you make that publicly accessible, it's even better, because then people can see the audit trail associated with your computer code. The second recommendation is make the data publicly accessible as well. Make all of your input data available. Right? In many cases with our energy system models, there's a distinction between the code and the data. And the code is basically a generic optimization framework that can operate on any data set. Okay? So it's not enough to just release the source code, you have to release the data. That then those two things combined allow us to replicate analysis. And better yet, if you can archive published data associated with a particular study, that's even better, right? So take a snapshot of the code and the data used to produce a particular journal paper or report, and then you've got a fairly precise accounting of what you did. The third recommendation is make transparency a design goal. It's great to make everything publicly accessible, but it's unlikely that someone's going to try and recreate everything from your source code alone. You need to provide some indication of what it is that you did. Right? So this often comes in the form of documentation. Many models do have documents, technical documents, that describe how they work. Okay? So it could be a standalone comprehensive document. You could also embed comments in the source code, right? So if someone's scrolling through, they can see exactly what this equation is meant to do. And then just well-designed code. So instead of naming things, X and Y in the code, give them descriptive names so that someone reading it can figure out the meaning just by the way that you name things. Recommendation 4, utilize free software tools. To the degree possible, don't use commercial software, because it just means money has to be spent in order to do the analysis, and particularly in an academic environment where perhaps a master's level student wants to just do some experimentation. I mean, they're not going to be able to pay $1,500 for a commercial license. So I think what we want to do is, where possible, use cost-free software to minimize the barriers to entry. Same thing in developing countries. Right? Many developing countries don't have large budgets to do energy modeling. In some cases, you might need commercial software. So for example, we use Cplex to solve some of our larger stochastic problems. But we always maintain a baseline model that can be solved with an open source solver. Okay? So at a minimum, make sure that some baseline version of the model can be solved with free tools. Recommendation 5 is develop test systems for verification exercises. This is an idea that's borrowed from electrical engineering. The IEEE has a reliability test system. It's essentially a system of power plants and transmission lines and buses that are used to evaluate techniques for assessing electric load reliability. Right? So every time someone does some analysis where they're looking at a different technique, they use this test system, and everybody knows what that test system is. It'd be really nice if we had something equivalent to this in energy modeling. Some well-defined, well-understood test systems, so that as we make changes to the code and so forth, we can run these simple test systems and verify that we're getting the results that we expect. Okay? It would also aid intermodel comparison, because if we can both run the same model, but run the same data set through different models, it can help us get to what some of the key differences are. Recommendation 6 is work towards interoperability of models. Again, kind of goes along with what I just said. But it would be really nice if we could develop generic data sets that worked across different models. Okay, so one of my ideas that I would love to see happen someday is to build a big relational database with all of the data that we've been talking about over the last 4.5 days, and then have a layer on top of that that can basically query the database, pull the data out, and then format it in the native format for each model. Right? So that we could all be working from the same data and the same assumptions. Right? Now there's lots of details to be worked out here, but it would be really nice to have that someday. And then finally, recommendation 7. This wasn't in the paper, but it was, I think it's just kind of my general philosophy, is build the model to be as simple as it possibly can be to answer the question at hand, but no simpler, and then expend the computing power to do the uncertainty analysis. So hit the model hard with uncertainty analysis to try and figure out how much variation there is in the results. Okay. Oh, how am I on?
A few minutes.
Few minutes? Okay. Okay. All right, so I'll go through this relatively quickly. We developed our own open source model called TOMOA, which is Tools for Energy Model Optimization and Analysis. And we were searching the internet to make sure it didn't mean anything bad, that we weren't choosing some word that we were going to regret. And it turns out that in the Aztec language, it means to seek something. So we thought, wow, this is a sign or something that was a good choice. So, long story short, our approach implements many of the recommendations that we talked about, right? So open source code, open data. We haven't gotten super far yet. We have published a paper that explains the model. It includes some analysis, and we've actually archived the source code and the data associated with that analysis in case anybody wants to reproduce the results, okay? Another important point here is that we designed it to work in a high-performance computing environment so that we can do that uncertainty analysis. So I already talked about this. This, again, is just to kind of refresh your memory on the kind of modeling that we do, but since I already presented it, I'm going to skip it. These are some of the features of the model. Again, not super critical to talk about. This is one of the results from our 2013 paper, and what we did was a very careful verification exercise where we used a data set that's packaged with the Markal model called Utopia, and we tried to very carefully replicate the exact result that they got, and we found something very interesting. So the Markal results are in black, our results are in white. And it doesn't matter what the labels are here. So there were 3 time periods in the model. This is showing petajoules per year of installed capacity. Don't worry about what the actual technologies are, but the bottom line is that the results didn't match. And we beat our heads against the wall for a long time trying to figure out why. And we realized that it wasn't our problem, it was Markal's. And essentially what it boils down to is if you have a demand device like a lighting system, or better yet, think of a heating system, right? The way that Markal works is it says if you have 100 petajoules of demand, it assumes that in order to calculate the capacity of that heating system, that those 100 petajoules are evenly distributed over the year. Ours says, no, you have 100 petajoules, but you told me that you're only going to use the heating over half the year. So we would need double the capacity. We think we're right, and if we are, do you know how many analyses have been done where the demand device capacity in Markal has not been calculated correctly? So again, it shows how important verification is. It's not the most exciting thing to do, but it really has a lot of value. Okay, in terms of what we're doing with uncertainty analysis, I'll just go through this very quickly. One of the things we'd like to do is stochastic optimization, and this is something we're working on right now. Let me see if, let me just skip to this one. So decision makers need to make decisions before uncertainty is resolved, right? They don't have a crystal ball. So we should be delivering them insight that accounts for that future uncertainty. So we're looking at a sequential decision-making process that allows recourse. So instead of having distinct scenarios, so here's high gas prices, here's reference gas prices, here's low gas prices, what if instead you build an event tree where those possibilities are embedded in the event tree and we assign them probabilities, and then we just optimize over the whole thing, okay? What will happen is all of the possibilities over here will affect, when you run the optimization, what happens here at the root node, okay? So this is kind of the unified strategy. Before we start resolving uncertainty, we develop a strategy here that hedges against the future risk. Okay, so for example, maybe it's easier if I go to this slide. So here's a very simple 2-stage process. We're at stage 1. The uncertainty has not been resolved yet in going from stage 1 to stage 2. So when we encode this into an optimization problem, here's the objective function, which is just cost. This is the first stage cost. Okay? You notice there's no dependence on what happens, whether scenario 1 or scenario 2 is realized. And then we weight the two-stage outcomes by their probability. Right? So these scenarios in the second stage are going to influence what I do in the first stage. It presents a hedging strategy. So if I'm trying to make a decision between natural gas and coal, maybe what I do in the initial, but I'm worried about how prices might be resolved over the next decade, let's say. The hedging strategy might be build a little bit of both, let the uncertainty resolve itself, and then take the appropriate recourse action. Okay, so that's the basic idea behind stochastic optimization, and that's something that we're exploring. The basic idea is you take the uncertainty, and instead of making a bunch of exogenous assumptions and running different scenarios, you incorporate that information into a single run.
So Joe,
Yeah.
can you quickly go to the conclusion because won't have time.
Yes. Okay. Yes. There's one more thing that I want to talk about. That deals with parametric uncertainty. There's also structural uncertainty, which I haven't talked about. So if we have a single objective model, I solve it, I get an optimal result, right? Well, in the real world, we have multiple objectives, right? So let's say that I convert my one objective model into a two objective model, and I create this non-inferior frontier. And perhaps I decide that this is the best place to be, right? So this is the optimal solution when I change my single objective model to a dual objective model. Well, if I project this solution into the solution space of the single objective model, you notice that it looks suboptimal. So what this means is that there's value in exploring the feasible near optimal decision space to see if there are alternatives that make sense. So we've been applying a technique called modeling to generate alternatives that allows us to do this. And basically what it does is it uses the initial solution as an anchor point, and then it explores the feasible region near that optimal solution and generates a set of maximally different alternatives. Okay? So I'll skip this. This is basically just the how the algorithm works. It's relatively simple. This is a sample result from a paper that I published in 2011. And this shows installed capacity for a very simple electric sector optimization problem. And the main point I want to make here is this is the base solution. These are the MGA solutions. These are generated by the computer, okay? Not by me. So what's interesting about this is it takes the idea of scenario analysis and turns it on its head. I'm allowing the computer to tell me what alternative solutions might look like. So I'm willing to let the cost increase by 10%, tell me what else I can do. And then as an analyst, as a decision maker, I can go through and say, wow, geez, I didn't realize that for just 5% more cost, I could actually swap out, one technology for another. Right? So it leads to additional discussion and analysis and insight. Okay? But it's scenarios that are generated by the model itself. All right, so these are the conclusions. In the interest of time, I'll just leave this up here without stepping through each of them, and I'd be happy to take any questions.